Welcome to today's video. Today we are going to explore a very fascinating topic in the field of quantum mechanics. The topic is fractional quantum Hall effect and its connection to exotic states of matter. So before starting fractional quantum Hall effect, we should know classical Hall effect. We should have some idea about classical Hall effect. Classical Hall effect, this was discovered in the year 1879. And according to this, a voltage develops when a current flows through a current carrying conductor in the presence of a perpendicular magnetic field. So this is known as a classical Hall effect, and this was discovered in the year 1879. Now fast forward to 1980, means there is a gap of 101 years. 1980. In the year 1980, integer quantum Hall effect was discovered by Klaus von Klitzing, a physicist. And according to this, Hall resistance is quantized into discrete values under at extremely low temperatures and under strong magnetic fields. Strong means very strong magnetic fields. So temperature should be very low and magnetic field strength should be very high. So in such a case, this phenomenon occurs, known as integer quantum Hall effect, where Hall resistance is quantized into discrete values. Later, means there is a gap, okay. Later, one new phenomenon was discovered. That new phenomenon is known as FQHE, or fractional quantum Hall effect. So the previous one was known as integer. Okay, you know the meaning of integer. And here fractional, this is being used. That means here the fractional filling factors are there, like 1/3, 5/2, 2/5. These values. What is this? Here, when this is studied, this is completely a new phenomena. Better to say, this is an emergent phenomena in the field of quantum mechanics. And this also happens at extremely low temperatures, like 4 Kelvin. Extremely low temperatures and strong magnetic field. Okay, condition remains the same as integer quantum Hall effect. So what is the new thing here? Here quasi-particles are observed. Quasi-particles, you know the meaning of quasi. Quasi means semi. Quasi-particles are observed. And what is the most intriguing to the scientists was what? The particles carry a charge of 1/3 of the electrons when the fractional filling factor was 1/3. I have already mentioned that fractional filling factors are observed like 1/3, 2/5 or 5/2. So in the 1/3 fractional quantum Hall state, the particles carrying charge, means electric charge, was equal to 1/3 of the charge of an electron. So this is a new phenomenon. Here what happens, the individual behavior of electrons, that is known to everybody. But here the collective behavior of electrons are totally different in such a condition where temperatures are extremely low and the magnetic field strength are extremely high. In such a case, the collective behaviors of electrons are completely different. So one thing we can see that charge carried by them is only 1/3 of the charge of an electron. This is new. And there is a chance, there is a possibility, scientists are finding possibilities that this new phenomenon can be used in the development of quantum computing systems. Again, in the development of new materials this concept or this phenomenon can be used. Here the collective behavior of electrons, or better to say quasi-particles here, the nature or the behavior of quasi-particles cannot be studied or cannot be explained by using the theories of classical physics. Here new physics is required. What is that new physics? It's a combination of the principles of quantum mechanics and topology. You know topology? Topology is a branch of mathematics where space is continuously deforming, and how the continuously deforming space preserve its properties. That is the matter of study in topology. Okay, so the help of means it's a combination of quantum mechanics and topology, the branch of mathematics. Together, this can be used. Actually, this is used to explain this new phenomena of FQHE, fractional quantum Hall effect. Topological nature of this matter means collective. I am talking about electrons. Collective behavior of electrons depends upon the topological nature. Means minor impurities or minor disturbance to the system cannot change its property. So this is known as here topological nature. And scientists are means according to them, this theory or this phenomenon can be used to peep through the window to the world of exotic states of matter. Exotic states of matter, that is not real. Okay, that concept you can study in the field of theoretical physics. But at present, there is no evidence of exotic states of matter. But there is a similarity in the behaviors of quasiparticles and exotic states of matter. That's why scientists are considering these quasiparticles as a window to the world of exotic states of matter. But this has already been discovered. FQHE means quasiparticles have already been discovered, and this is being used in the development of new materials. And there is a great possibility of using this phenomenon in the field of quantum computing. So what is the new thing here? New thing is here, electric charge carried by them is only 1/3. In case of 1/3 fractional quantum Hall state. Examples are phonons, magnons, excitons. These are the examples of quasiparticles. One more thing, you know, there is different science or different physics to describe the behavior of bosons, to describe the behavior of bosons and fermions. Means bosonic statistics is there, fermionic statistics is there, and they are different. Again, these quasiparticles, the behavior of these quasiparticles found in the case of FQHE, these the behaviors of these quasiparticles cannot be described by using either bosonic statistics or fermionic statistics. A new statistics is required known as anionic statistics. That is used to describe the behaviors of what? Of these quasiparticles found in the experiment. Okay. So, this was all about today's topic, fractional quantum Hall effect and its connection to exotic states of matter. Okay. Okay, so this is the end of this video. Thank you. Thank you for watching this video.